For splitting pattern, I will give you this first example, which is very easy. As you can see, we have three types of hydrogen atom, this molecule. First type is in aromatic region. Actually, in aromatic, there are three subtypes of hydrogen atom, which is ortho to the substituent, meta to the substituent, and the para to the substituent, right? But this hydrogen atom splitting with this one, right? Because there are different type of hydrogen atom, so they have kind of splitting pattern. So they split with this one, and then this one can also split with both type of hydrogen atom, right? The meta position here split with ortho and split with the para, and the para triplets splitting with the two of the meta over here. So as you can see, they are splitted all together, but all of these appeared very close together at about 7. So we cannot kind of clearly see this pattern of splitting over here because they're just too close together, right? But anyway, from the integration, it is 5. Right? So we're quite sure that this is monosubstituted benzene over here. But what I want you to see is these two peaks. The CH2 and CH3 confirmed by the integration 2:3 ratio. And because CH3 are very far apart from the aromatic, so it is 1. This yellow color is one atom far from the aromatic. You have one carbon over here, right? So instead of appearing at 7 ppm, you have this carbon in the middle, so it's dropped to 2 ppm. And the integration is 2:3. The yellow color over here is now splitted with the purple color. We have 3 hydrogen, so splitted to be quartet, 4 peaks, right? 1 to 2 to 2 to 1 ratio, and the purple color is splitted by the yellow color. So we have 2 yellow color, so it splits the purple color into 3 peaks as triplet, right? It's like this. So I show you the purple color over here is splitted by the first yellow into doublet, and then each of the peaks are splitted again by the second yellow to doublet and doublet, right? Because they are appear at the same place, so it's twice the height. So it's 1 to 2 to 1 ratio triplet, right? So this is why CH3 appeared as triplet. So as you can see here, you can, if you see quartet and triplet with 2:3 ratio, you can be quite sure that it is the ethyl group, right? Because if you have ethyl group, the yellow of the ethyl splitted triplet by the purple color, and the purple color is the yellow color is quartet by the purple color, and the purple color is now splitted to be triplet by the yellow color. So both the peak height, the integration peak area, and the splitting pattern can confirm that this is the ethyl group. Now we're going to the next example over here, C5H10NO. C5H10O, first of all, what you have to do is find the dBe. So from this, dBe is equal to 1. So it can be a double bond or a ring. Okay. So if you look at the integration, because in summarize, you have 10 hydrogen atom, and this is 1, 3, 6 is 10, right? And of course, because you have 3, so this have to be CH3, and you have 6, so nothing else rather than 2 of CH3. And if you look at the CH3 over here, this CH3 appeared as singlet. That means the CH3 over here has no hydrogen nearby, has no neighboring hydrogen, and because it's appeared at 2, and you have O. So you may assume that you have the ketone. right? You have carbonyl because hydrogen atom next to the carbon of carbonyl is about 2 ppm. So I would put CH3 over here. So it's very makes sense because this hydrogen has no neighboring hydrogen atom, so it appeared as singlet at 2, right? But then we have this singlet. No, not singlet. One hydrogen atom at 2 ppm as well. So this have to be CH, right? CH, and this CH at 2 ppm. So the green would be something like this. So we already used 3 carbon atoms from 5, right? And we have 2 of CH3 left. So as you can see, both CH3 connecting with CH green, only one H. So it splitted the pink into doublet, right? While your green here is splitted by 6 of the hydrogen. So this green appeared as 7 peaks, right? So we call this as septet. 1, 2, 3, 4, 5, 6, 7. That's it. It is so easy. So the previous one, you see the quartet and triplet with 2 to 3 ratio. You sure that this is ethyl group. For this case, you saw the multiplet and doublet in 1 to 6 ratio. You can be sure that this is the isopropyl group. Okay, so this is isopropyl character, and the previous one is the ethyl character. Okay, so we're gonna move on to the next one. This is nitrotoluene. So nitrotoluene, what is the nitrotoluene? Nitrotoluene is this is the benzene, right? Toluene is meaning that you have CH3 connecting with the benzene. This is called toluene. But if you have nitrotoluene, you have nitro group over here. But nitrotoluene, there are 3 different isomers. That means you have this one as para-nitrotoluene. And then you may have meta-nitrotoluene and also the orthonitrotoluene. I will list it here in the picture. So we have CH3, we have CH3, and we have nitro group here and here. NO2 over here, NO2 over here. So there are 3 possibilities of the structure of nitrotoluene. The question is, which one belongs to this spectra, right? So it's very easy. As you can see, we have CH3 at about 2 ppm. So this is the character of CH3 connecting with the connected to the benzene ring, right? Now, so for the orthonitrotoluene, you have this hydrogen, you have this second type, you have third type of hydrogen, and you have fourth type of hydrogen. So you have 4 different type of hydrogen atom around the aromatic ring, right? But look at the picture over here. You have only 2, right? 2 types of hydrogen at 7 something and at 8 something, and 2 of them, these 2, splitted together to be doublet and doublet, right? So it's impossible to be ortho position, because for ortho position you have 4 different hydrogen types, and they have splitting, quite complicated splitting. As you can see, one split by 2, right? The second hydrogen over here splitted by number 1 and number 3, right? So it's very complicated. So it's impossible to be this ortho position. So I just get rid of them. Now we look at the second possibility, no? So you have H number 1, H number 2, H number 3, and H number 4. Again, you have 4 different types of hydrogen atom. This is singlet. This is triplet because coupled with 2 and 4, right? Number 2 and number 4 appeared as doublet. But what you can see over here is nothing about this. So it's actually this one. So now you have to identify. You have purple color H, and you also have the yellow color H, right? So the purple color H and yellow color H, they coupled, right, as doublet and doublet, because the purple color you can see only one hydrogen nearby, right? So it's split it into doublet, and the yellow color split it to doublet as well. Now, can you gauge which signal is purple, which signal is yellow? This is the next step, right? As you know, nitro group is the electron withdrawing group, and the methyl group up there is the electron donating group. You have electron withdrawing, you have electron donating properties. So it resonates electron into your benzene ring. So for nitro, as electron withdrawing, right? So it withdraws the electron from the benzene ring like this. And by this resonance structure, you can see that this carbon is now positively charged, right? This is the resonance structure of the nitro, no? So like this. So by positively charged over here, it withdraws the electron clouds from your hydrogen. So hydrogen is now deshielded. So this hydrogen should appear on the left hand side. So this confirmed that the yellow color hydrogen is on the left hand. And also the purple color appeared on the right hand because of the electron donating of a property of methyl group. The methyl group using hyperconjugation effect, if you can remember. So by hyperconjugation effect, it donates electron into the ring. So electron in the ring resonance up to the carbon on the ortho position, right? And make this carbon negatively charged. So brings the electron clouds around here. So hydrogen is partially shielded by the electron clouds, dense electron clouds, right? So by look at the resonance effect, we can now predict the position of yellow and purple color hydrogen atom. Okay, this is useful for the very complicated structure. But if you look at it, just the splitting pattern, you can know what is the isomer of nitrotoluene here, right? And this is the para isomer. Now come to the another question. So as you can see, I want you just identify which hydrogen is which signals, right? So first of all, we have how many type of hydrogen? 1, 2, 3, 4, 5 hydrogen, right? So first hydrogen type is the methyl group down here. So it's 6 hydrogen atom. So it is very obvious that we have 2 of the CH3 appearing at 1 ppm because the integration of the peak area is so high. And then we have 1 to 1 and 2 to 2 over here. So 1 to 1 is this 2 in the right hand side, and 2 to 2 ratio here is the left hand side hydrogen atom, right? So which is very obvious because these two are the alkene, so appears around 5 to 7. These two are the alkane, so it appear around here at about the alkane region. But now we are going to look at deeper in detail. So we look at the alkane first. So in the alkane side, we have green and we have yellow, right? And as you know, the yellow color over here is next to the carbonyl, so it appear at 2 ppm. So 1 ppm is green, and then 2 ppm is yellow, right? It's very obvious. Now, how about the alkene side? So for alkene side, you have red color, and you also have the, which color? Maybe this one, the shit color, the brown color, sorry. So, but the effects over here are different from the alkane things, because now the double bond is conjugated with the carbonyl. So if you draw the resonance structure, if you draw the resonance structure like this, you can see that the resonance structure is like this, right? The brown color hydrogen atom is attached to the carbon with positive charge, so this is deshielded, right? Electron cloud is less than the red one. So the brown with less electron cloud, that means the external magnet can interact with the brown color strongly. So it is very hard to excite it to the excited state, required higher energy, right? So the brown color appear at the higher energy zone on the left hand. And then the red color appeared on the right hand. That's it. So this can be described by the resonance structure of the O-key. Okay. Now I will give you another example. Okay, last question. You may pause here, right? For the question is, this is C9H10O2. So please find the structure of this molecule using only this IR splitting pattern. Okay, so I'm going to give you the solution. So I want you to do it by yourself. So pause the video right here. Okay? After you finish, then come back. Okay, so if you finish, we're going to look at this one. First of all, when you see the molecular formula, so first of all, what you have to do is find the DBE. So the DBE of this case, carbon minus hydrogen divided by 2 plus nitrogen, but you don't have nitrogen, no? Plus nitrogen divided by 2 and then plus 1. Oxygen is not in the formula. So it's 9 minus 5, which is equal to 4, right? And plus 1, so it's 5. DBE 5, and you have the aromatic region over here, right? 7 to 8 is aromatic region. So one aromatic ring is one ring with 3 double bond. So you use already 4, right? You use already 4 DBE. You have only 1 DBE left. And this 1 DBE can be many things. So we'll come back to see about what is about the 1 DBE later. But anyway, because the number of hydrogen is 10, so now you have to approximate from the peak height. Okay. So from the peak height and the sum up have to be 10. As you can see, this 2 peak is higher than this 2 peak, a little bit higher, not the double, right? So it should be 2 to 2 to 3 to 3, right? 2, 2, 3, 3, and then it is 10, right? Perfectly. So as you know, 3 is CH3, right? So you have singlet CH3 over here. You have singlet CH3 over here. Okay? And what else? This singlet CH3 is at 4 something. 3 something, very nearly, very close to 4. That means hydrogen over here have to attach with very high En. Right, if you can remember. But from the structure, from the molecular formula, the high En element over here, only oxygen atom. So it have to be oxygen over here. So this is methoxy group appeared as singlet. So this methoxy group is reasonable. Now, if you look at CH3, there's no coupling, right? This one is singlet. So this CH3 have to attach with anything without hydrogen atom and 2 something. There are just 2 possibilities, because 2 something meaning that this CH3 attached to aromatic, or it may also attach with carbonyl, right? Whether it's carbonyl or aromatic, it appeared at 2 something as well. So we don't really know whether this is aromatic or carbonyl. But anyway, at aromatic region, as you can see, the integration is 2. And they coupling together like this. So the only possibility to have this kind of thing is they just couple together, right? We have 2 types of hydrogen atom coupled together. So it have to be something like this. You have like I would say disubstituted aromatic, right? So only disubstituted aromatic, you can have this doublet and doublet together, right? So now what we have here is we have CH3 attached with aromatic OMe bicarbonyl. You have methoxy over here, you have aromatic over here. So you have 6 carbon, 7 carbon, and 8 carbon. You have only 1 carbon left, right? And you have 1 oxygen left, and you have 1 DBE left. So that means you have carbonyl, nothing else. It have to be carbonyl. So we have carbonyl, we have purple color CH3, we have yellow methoxy, and we have aromatic. You just mix all these things up together. So what is the structure of the molecules? Actually, there are 2 possibilities. First possibility is your benzene ring over here attached with OCH3, and then you have carbonyl, and then you have CH3. This is the first possibility, right? And another possibility is you have benzene ring, you have carbonyl, you have OCH3, and you have CH3. Because both of these CH3 appeared at 2 something, right? This is the purple color CH3. It have to be like this, CH3 and CH3, right? The methoxy group, pink color, yellow color methoxy group can be, oops, sorry, this is OCH3, can be like this, OCH3 can be like this, right? And that's it, because we cannot really know whether the purple color attached with carbonyl or attached with aromatic. So we have just this kind of 2 possible structure, right? And that's it, nothing else we can do. And if I want to ask, how can you know whether this is the first molecule A or the second molecule B? What should you do? What kind of techniques do you have to do in order to identify whether this graph belong to A or belong to B? Give you 5 seconds. Okay, so we have to test, right? We have to test. We have so many kind of tests. If you can remember some of the chemical reaction, you can do the iodoform test to find the CH3 attached with the carbonyl. You can do the iodoform test, find the white precipitation of iodoform by treating the molecules with iodine in very strong hydroxide solution, very strong base. And if you have the white color precipitation, is the A. If you don't see the white color precipitation, it's the B. But you can also use the IR techniques, right? Because this is a carbonyl, this is the ester. Oh, but it's quite difficult because the carbonyl normally appeared about 1700 something, but it's resonance with the benzene ring, so it's dropped down to 1600 for sure. But this is the ester appearing at higher than 1730, but you have resonance, so it's dropped down under 1735 something, but it should be higher than 1600. So if it's less than 1600, it should be A, and if it is higher than 1700, it should be B, right? So there are these kind of things. Or you can also look at the mass spectra as well. The mass spectra for the B, you can cut this one off very easy because you will have the neighboring group participation to stabilize the carbocation, and this should be the base peak, the base peak. And for the A, you should cut only CS3 in order to stabilize with the neighboring group participation like this, right? So the base peak appeared at a different position. This is the example of how we can use spectroscopic techniques to identify the molecular structure. Okay, so now I want to end our proton NMR spectra over here. Next topic will be carbon-13 NMR spectra. So see you again in the next video. Thank you very much for today.